Hello everyone and welcome. Today we are going to explore one of the most fundamental and intuitive algorithms in machine learning, that is k-nearest neighbors or KNN. So what is k-nearest neighbors? At its core, it's a simple supervised machine learning algorithm built on a very intuitive idea. You are what your friends are, or more technically, similarities exist in close proximity. In practice, this means we classify a new data point by looking at its k closest neighbors from the data we have already seen. The algorithm then takes a majority vote from those neighbors to decide what class the new point belongs to. KNN is famously known as a lazy algorithm or an instance-based algorithm. This is a key concept. Unlike other models, KNN doesn't have traditional training phase. It doesn't build a complex model. It simply memorizes an entire data set. All the real work, the distance, calculations, is postponed until the moment we ask it for a new prediction. Let's make this crystal clear with an example. On this slide, see a data split into two classes. Class A, the blue dots, and Class B, the red dots. Now, a new unlabeled data point appears, the one marked with a question mark. We need to decide, is it blue or is it red? For this example, we have set our k value to 3. This means the algorithm will find the 3 nearest neighbors to our new point. The dashed line point to these 3 closest neighbors. Now, we hold a vote. If we count those neighbors, we find 2 red dots and 1 blue dot. With 2 votes for red and 1 for blue, red wins the majority. Therefore, the KNN algorithm classifies this new point as red. It is as simple as that. Find the neighbors, hold a vote. Let's formalize this into a clear step-by-step algorithm. First, we choose a value for k. This is our main setting or hyperparameter. Second, when a new point arrives, we calculate the distance from this new point to every single point in our training data. Third, we find the k nearest neighbors by sorting all those distances from smallest to largest and picking the top k. And finally, we make the prediction. As we have discussed for classification, we take a majority vote for regression. We take the average of the neighbors' values. The most important choice we have to make is what is k. K is simply the number of neighbors we look at, and choosing the right k is a critical balancing act. Let's look at the example on the slide. We have set k is equal to 5. When the new black point appears, the algorithm finds its 5 nearest neighbors in the vote. There are 3 green neighbors and 2 red neighbors. Green wins the majority, so the black point is classified as green. But what if we choose k is equal to 1 or k is equal to 25? This is where we see the trade-off as shown in the table. If you pick a small k, like k is equal to 1, the model becomes highly sensitive to noise. It might just pick one weird outlier as its neighbors. This is called overfitting. If you pick a large k, the model oversmooths the data and might miss local patterns. This is called underfitting. This slide is the perfect visual for the exact concept. On the left, we have k is equal to 1. Look at that decision boundary. It's incredibly jagged and complex, twisting and turning to perfectly fit every single data point. This is classic overfitting. It might be 100% accurate on the training data, but it will fail to generalize to new unseen data. On the right, we have k is equal to 15. The boundary is much smoother and more in general. It captures the overall trend of the data. This is much better, more generalized model that will perform better on new data even if it misclassifies a few training points. So, if k is equal to 1 is bad and k is equal to 15 might be bad, how do we find the best k? We can't just guess. The most common technique is called the elbow method. The process is simple. We run our KNN model multiple times with a range of k values. Say k from 1 to 20. We then plot the k value on the x-axis against the model's error rate on the y-axis. You will almost always see a graph like this one. The error drops very quickly and then it flattens out. The ideal k is the elbow, the point where the curve sharply bends. In this graph, that's clearly at k is equal to 3. This is the point of diminishing returns where increasing k any further doesn't really improve a model. Alright, let's move from theory to practice and see what it looks like in Python code. This first slide just shows our necessary imports. We are importing NumPy from numerical concepts. We are importing matplotlib and seaborn for data visualizations. And most importantly, we are importing everything we need from scikit-learn or sklearn. This includes datasets, our train test split function, the standard scaler, the k-neighbor classifier itself, and performance metrics. Next, we load and prepare our data while using the famous IRIS dataset. Crucially, you will see we are only selecting two features, petal length and petal width. We are doing this only so that we can easily plot our results in a 2D graph later. We then split our data into training set and testing set, with 70% used for training and 30% for testing. This is a standard practice to ensure we can test a model on data it has never seen before. This next step is one of the most important steps for KNN, feature scaling. We create a standard scalar object. Then we fit the scalar only on the training data. This learns the average and standard deviation of a training set. We then use that same learned transformation to scale both our training data and our test data. This is critical to prevent data leakage. We must always pretend we don't know anything about the test data, including its scale, when we are testing. And now, the main event. First, we set our k value to 5. Second, we create the k neighbors classifier object. Third, we train the model knn.fit. Remember, for KNN, this step is almost instant. It's just memorizing the data. Fourth, we make predictions on our unseen test data using knn.predict. Finally, we print the classification report and look at that. We have 100% accuracy. The precision recall and the F1 score are all perfect. This tells us that for the iris dataset, petal length and petal width are extremely good features for separating this flower species. This final block of code looks complex, but it's all doing is generating the beautiful visualization you see on the right. It creates a grid, predicts the class for every single point on that grid, and then colors the background based on those predictions. The plot itself is the visual proof of our model's performance. The colored regions, red, green, and blue, are the decision boundaries our model has learned. The circles are our test data points. And as you can see, every single test point falls within its correct colored region. This visually confirms our 100% accuracy. Earlier I said the algorithm calculates the distance, but how exactly does it do that? The nearest in k nearest neighbors can be measured in few ways. The most common is Euclidean distance or L to norm. This is the one we all learned in geometry. It's the straight line. As the crow flies, distance between 2 points. This is default in most libraries. Another popular method is Manhattan distance or Elven norm. This is also called city block distance. Imagine you are in a city grid where you can only travel along horizontal or vertical streets. You can't cut diagonally. It's simply the sum of the absolute differences of the coordinates. This image perfectly illustrates the difference. The Euclidean distance is the green line. The direct straight line shortcut from point A to point B is the shortest possible path. The Manhattan distance is the path you, you would actually have to walk in a city, like the blue, red, or yellow lines. You go over several blocks horizontally and several blocks vertically. The distance is the sum of those moves. The choice of metric can actually change which neighbors are considered closer. I mentioned this during the code walkthrough, but it's so important it deserves its own slide. Feature scaling. It is a critical non-optional step for KNN. Why? Because KNN is based entirely on distance. Imagine you have two features, age, which ranges from 20 to 70, and salary, which ranges from 50,000 to 200,000. If you don't scale your data, a difference of 20,000 in salary will completely dominate a difference of 20 in age. The algorithm will think the salary features is thousands of times more important simply because the number is bigger. Look at the graphs. Without scaling, the salary axis stretches so far the age axis is compressed. The distance calculation is completely biased. With scaling, we put both features on the same scale. Now both age and salary contribute equally to distance calculation, and the model can find the true nearest neighbors. Finally, let's summarize the good and bad of KNN. On the plus side, that are the advantages. It's simple and intuitive. This is its greatest strength. It's very easy to explain to a non technical audience. There's no training phase. It's a lazy learner, so it's great for systems when new data is added constantly. It's flexible, working for both classification and regression. And it's non parametric, meaning it makes no assumptions about your data shape. On the downside, disadvantages, it is slow at prediction time. This is its biggest weakness. It has to compare a new point to every single point in the dataset. This is not suitable for large scale real time systems. It needs feature scaling. As we just saw, this is not optional. It needs to store all the data. It has to keep the entire data set in memory, which can be problem for large data sets. And finally, it suffers from the curse of dimensionality. In a very high dimensional spaces with hundreds of features, the concept of distance becomes less meaningful and KNN's performance gets much worse. And that concludes our overview of K nearest neighbors. KNN, an intuitive proximity based algorithm for classification regression that does not require a separate training phase. The choice of K dramatically affects the model's performance. Very small k leads to overfitting with complex boundaries and poor generalization. Large k produces smoother and more general boundaries that may underfit. Optimal K should be selected by validation, not just by training accuracy, and feature scaling is critical for KNN. This was all we discussed today. Thank you very much. Thank you.